Alright, so in this problem, we drop a ball from a window on an upper floor of a building and it is caught by a friend on the ground when the ball is moving with a speed of velocity final. Now, you repeat the drop, but you have a friend on the street below throw another ball upwards at a speed velocity final at exactly the same time that you drop the ball from the window. The distance between the two balls is 28.7 meters. So I'm going to go ahead and draw a picture of this. So I'm sitting out here, hanging out this window safely, and I am going to drop a ball down to the ground. I then have a friend down here who is going to throw a ball upwards. So I'm going to label this ball A, and this is ball B. Because these are two different objects, I'm going to consider their motions separate from each other. So, for ball A, I know that I drop the ball from the window. So this means that its initial velocity is going to be 0, because I'm dropping it, I'm not throwing it, and its final velocity is going to be VF. Then for ball B, I know that its initial velocity is going to be VF, where this VF and this VF are the same. So I'm actually going to put like a little subscript, VF1, VF1, so that I know that these are going to be the same value. The two balls are initially separated by 28.7 meters. So the distance of separation, I'm going to call this the distance between them, is 28.7 meters. I'm using distance instead of displacement because one ball is going to be going in the positive direction, the other ball is going to be going in the negative direction, and honestly, I don't know if I am considering the ground to be y is equal to 0, so I'm just going to call this distance for now. And we want to figure out at what time do they pass each other, and at what location do they pass each other. I'm using y because I want location. So this is going to be a kinematics problem. So I'm going to write down my kinematic equations. So now that I have my kinematic equations written out, I have to pick somewhere to start. I also know that these are going to be acting in a normal universe on Earth, so we will have acceleration of negative 9.81 meters per second squared for each of those. So the first thing I want to do is I want to find the time that they pass each other. I think that I'm going to end up having to do a system of equations for this, just because I don't have very much information. I have acceleration, I have an initial velocity, but I don't have time, I don't have like a location where it will be whenever the objects pass each other. I don't have a final velocity, right? I just have a variable. I don't have time. Again, I don't have locations, I don't have time, I don't have a final velocity, and I don't know what the change in position is going to be for the object going, for example, from object A going to where it encounters object B. Like, I don't know what this location is. So I'm going to have to just take the information I have, and I'm going to make a guess. So instead of immediately trying to solve for time, I think I want to get more information about ball A. So I think the best approach is going to be for me to try to figure out what this final velocity is, whenever my friend on the ground catches the ball, so that I at least have more information. Because if I can figure out what the final velocity is of ball A, then I also know the value for the initial velocity of ball B, and that will help me figure out when they're going to encounter each other. So if I want to find the final velocity, I need to find an equation that contains final velocity, right? So 3 isn't going to work. But also, I don't have time, so I can't use the top 2 kinematic equations. I have to use this 4th kinematic equation. So my final velocity squared is equal to the initial velocity squared plus 2a change in position, their displacement. I know that this final velocity that we're not really given, that's stated in this problem, is the final velocity when my friend catches the ball. And if the 2 balls are initially separated by 28.7 meters, that means that when my friend catches the ball, my ball has been displaced 28.7 meters. So I can use 28.7 meters for this displacement, but it's going to be negative 28.7 meters because it is being displaced in the negative direction. So my final velocity is equal to plus or minus the square root of my initial velocity squared, which is 0, plus 2 times negative 9.81 times negative 28.7. And because the object is falling, I know that this velocity is going to be a negative value. And I get that my final velocity is going to be 23.7 meters per second. Now I'm going to rewrite all the information that I have for both of these objects, right? Because I have a little bit more information now. So I know that my initial velocity is 0. My final velocity is negative 28.7 meters per second. I have acceleration is negative 9.81 meters per second squared. For object B, I now know that my initial velocity is going to be 28.7 meters per second. It's going to be positive because this object is going to be moving in the positive direction, right? They're both negative, they wouldn't pass each other. And we still have, obviously, they're both encountering the same acceleration, and I have this distance between them of 28.7 meters. I'm wanting to find time, but I don't know at what location they're going to encounter each other. So I'm going to have to find a way to take 2 kinematic equations and connect them together, because I don't have enough information to solve this with one. So what I'm going to do is, instead of staring at that, I'm going to take a little bit of time and think through this. So, one of my most influential professors, Fred Leibsley, always said, if you don't know how to solve a problem, draw a bigger picture. So we're going to draw a bigger picture. So here's me. I have this ball, my friend has that ball. My initial velocity here is going to be 0. Whenever it gets to this location, my final velocity is negative 28.7. The initial velocity for this ball is 28.7. We don't know how far it's going to go up, but we know at some location they're going to encounter each other, and that will be the time that we're looking for. So one thing that I think that I can do in this situation is I can consider this initial position to be something, and this final position to be let's call it C. I'm just going to use a variable right now because I don't have a number. This initial position is something, and this final position is going to be equal to C, meaning that they both have the same final position at time t. I can use that as well as time to try to connect them together. So let's see what we can come up with here. I'm actually going to move my coordinate system so that this place is y equal to 0, right? So when my person catches the ball, I'm going to consider that y is equal to 0. That means that my initial position for ball B would be y is equal to 0, and my initial position for ball A is going to be that 28.7 meters. So what I'm going to do is I'm going to take my fourth kinematic equation, and I'm going to start working with it for ball A. So my final position is equal to the initial position plus the initial velocity times time plus 1/2 acceleration time squared. So remember that now I've labeled the final position for ball A as a variable C. I have an initial position. My initial velocity is 0, so that term will go away, and I will have 1/2 acceleration time squared. Sorry, my pen died. Okay, so I'm going to use a similar approach for ball B. So I'm going to have that y final is equal to y initial plus my initial velocity times time plus 1/2 at squared. My final position is also C in this situation. My initial position is now 0, so that term will go away. And now I have an initial velocity times time plus 1/2 at squared. Oh, this will work out well. Yeah, this will work. Okay, so a couple things here. These C values are going to be the same, but also this last term is going to be the same value, right? Because they both have 1/2. They're both being influenced by the same acceleration due to gravity, and they're both going to be traveling for the same amount of time. That means that I can move the 1/2 at squared to the left-hand side of both of these. So C minus 1/2 at squared is equal to y initial and C minus 1/2 at squared is equal to the initial velocity times time. Because these values are the same, I can set this equal to each other. This means that y initial is going to be equal to the initial velocity times time, and now my time for both of these is going to be equal to the initial position of ball A divided by the initial velocity of ball B. So I will have that time is equal to 28.7 divided by $23.7, and I get a time of 1.21 seconds. I can check to make sure this is correct by seeing what the final position of each of these is. So I'm actually going to take this and I am going to plug it into this equation and see what I get for y final, and then I am going to plug it into this equation and see what I get for y final. So if I plug it in, right, to equation A, I will get that y final is equal to the initial was 28.7 plus initial velocity of 0 plus 1/2 negative 9.81 times 1.21 squared. And I get that the final position is 21.5. And if I do the same thing over here, y final is equal to my initial position was 0. My initial velocity was, 23.7 times 1.21 plus 1/2 negative 9.81, 1.2, that's not a number, 1.21 squared, and I should get 21.5 again. And I also get that y final is 21.5. So because these are the same location, I know that my solution is correct. So this is the correct solution. All right, what's the next thing? Ask us. So it was 1.21 seconds. At what location do they pass each other? Oh, well, we just did that. 21.5. 21.5. Since I didn't actually work it all out, I'll do it again. So y final is equal to y initial plus vi times time plus 1/2 at squared. I'm going to consider this for ball A. So y final is equal to, the y initial was 28.7. My initial velocity was 0. 1/2 negative 9.81 times 1.21 squared. And when I plugged that into the calculator, I got that the final position was 21.5 meters. That is the solution for part B. I will say that there are a couple other ways to solve this problem. There are different kinematic equations that you can use. This is what made sense to me, was to solve it using this approach. No matter what, you have to use a system of equations because there's too many unknowns here. You're going to have two equations and plug one into the other. That's the only way to go about solving this problem. Which equations you use can change, but any approach is going to end up with a system of equations.